So yeah, I'm going to tell you about our recent efforts on low overhead error detection with the space-time codes. As we have seen in this conference, quantum error mitigation allows us to obtain bias-free expectation values from noisy quantum computers. However, this comes at a cost of additional sampling. In fact, the sampling overhead of quantum error mitigation scales exponentially with circuit size. On the other side, we have quantum error correction that does not have such a sampling overhead. However, it comes at the cost of very complicated hardware. We need many more high-quality qubits, long-range connectivity, real-time decoders, and so on. In this talk, the theme that I want to explore is charting a continuous path from quantum error mitigation to quantum error correction. So we can think of quantum error mitigation and quantum error correction as two ends of a spectrum, where we are trading off samples versus qubits, or trading off space with time. On one end, as I mentioned, we have error mitigation, which has exponential sampling overhead. And today, we can run thousands of gates using these error mitigation techniques, and they would allow us to calculate expectation values. On the other end, we need many qubits to perform fault-tolerant operation. There is no sampling overhead. We can run millions of gates, and this is a single-shot method. However, until we get there, we want to explore something in between. And that is where error detection comes in. Error detection uses extra qubits to reduce the sampling cost. It is also a single-shot method. Let's make this trade-off more quantitative. Consider an n-qubit quantum circuit with m gates being executed on a quantum computer with some gate error probability p. And we would like to boost the fidelity from f, which is 1 minus p to the m, it exponentially decays with the number of gates, to some other number, f prime, that is higher than f. In quantum error mitigation, as I mentioned, there is no qubit overhead. We don't need extra qubits. We just run the same circuit multiple times. But the sampling overhead, for example, for PEC, which is a bias-free method, is exponential in the number of gates. And in fact, it's 1 minus p to the power of m to the power of 4. And it's not a single-shot method. For quantum error correction, for example, surface code, there is no sampling overhead. We just have a qubit overhead that is in principle efficient. And it's a single-shot method. And quantum error detection has a constant qubit overhead. It still has an exponential sampling overhead. But the sampling overhead here is quartically better than the sampling overhead there. So this is very nice, but how do we do it? How do we detect errors? There are different ways. For example, we can verify symmetries. We can measure conserved quantities of a physical system. For example, spin parity, fermion particle number. In our application, we can find a suitable symmetry, measure those conserved quantities, and if those are violated, we can discard the shots. We can also use error detecting codes and encode qubits in a code. However, computations with such codes are not straightforward. We need to also build our fault-tolerant gadget. Finally, we have coherent Pauli checks. This is a method where we check whether a Clifford circuit correctly maps input Paulis to output Paulis. And this is the subject of this talk. Basically, if a Clifford circuit doesn't map the Pauli input to output Paulis as expected, we detect a fault, and then we can discard those shots. So what are these coherent Pauli checks useful for? They can be used to perform error detection in Clifford-dominated circuits. They work well when the circuit has a large Clifford or near Clifford chunk. Such circuits are in fact universal. Any circuit can be written as a Clifford circuit applied to a magic state input. Many quantum advantage proposals also involve Clifford circuits. For example, conjugated Clifford sampling or extended Clifford sampling use such circuits. In addition, we can create graph states using Clifford circuits. These are states that are hard to sample from and can also be used as a resource for measurement-based quantum computing. So how do we use coherent Pauli checks? How do we implement them? And how do they work? We start with a payload, the unitary here, that we would like to implement. And we can add a left Pauli and a right Pauli. And these two Paulis have to have a certain relationship between them, such that the overall evolution of the data qubits is unaffected. In fact, the right Pauli is the conjugated left Pauli by the circuit unitary. Now, once we find such Paulis, we turn them into a control Pauli and entangle them with a check qubit, an ancilla. What happens is that this input-output relationship that I mentioned would be violated if an error occurs here, and that error doesn't commute with the Pauli. So such error, the errors that don't commute, lead to a phase kickback, which would flip the ancilla, and then we can use this syndrome to discard the shots that had an error. So such controlled Paulis can also be implemented using localized Paulis, localized control Paulis. So we can implement them in principle. And we can also add more checks to detect more errors. But adding more checks with noisy hardware introduces new errors. So it is very important to probe for errors with low overhead checks. Otherwise, the checks introduce more errors than they detect. Okay? So the question is how we can actually do and implement these checks very efficiently. So this is where our new work on low overhead error detection with the space-time codes come in. So let's look at this Clifford circuit. This is our payload, and the blue qubits are our payload qubits, data qubits. These are all on a line. If we want to use this one-sided check that I mentioned, the just controlled right Pauli here, we need to entangle ancillas with our system qubits, and we need to swap them in because of those, as you saw in the previous slide, there were controlled Paulis all over. And as you can see, as we add more checks, the size of the check circuit exceeds the size of our original payload circuit. So this is not very efficient. However, with this new approach of space-time checks, we can find ancillas that are connected to our system and sprinkle them with Paulis in space-time such that the overall evolution does not change. But those sprinkled Paulis, when they turn into control Paulis, will detect errors for us. Okay? And there are two figures of merit that we really care about, the post-selection rate and the fidelity. So post-selection rate is the rate with which we discard these faulty shots. And as we detect more and more errors, it is expected that the post-selection rate would go down. And as the post-selection rate goes down, we are detecting more errors, so the fidelity will increase. The fidelity and post-selection rate, as I mentioned, are two figures of merit that we care about. But we don't want the post-selection rate to go down more than necessary. And now comparing these two methods, we can see that the new method has 1,000 times better post-selection rate. It gives us a 70% better fidelity, and it uses 2 times fewer gates. And these are the gates that we have to use to implement the checks. So the overhead is very mild in space. So let's see how these work. So we start with a payload circuit, and we identify an adjacent qubit that acts as a check qubit. And we have to identify some accessible wires. These wires are space-time locations that we can add Paulis. We then find valid low-weight Paulis supported on these wires. A valid low-weight Pauli, by that I mean that the Paulis that we put here should not change the overall logical operation of the circuit. So basically, they shouldn't do anything. They shouldn't change anything in the ideal scenario. We can also use a technique we introduced called back-cumulant to score these checks and evaluate the logical error rate, basically the amount of error we can catch if we implement such Pauli checks. And then we can use this scoring formalism to find the best checks and implement them using this control ancilla. And then we can repeat this whole process to find more checks. So I'm not going to get into the detail of how we actually do this and the algorithm, but I strongly encourage you to check out the tutorial in the afternoon for a hands-on experience with this method. So basically, these low overhead checks, they have a low overhead. There is for example, here, there are 3 wires that we chose. We add these checks, and in the green region, we can detect errors that do not commute with these Paulis. So we have a large detecting region with a very low overhead. And another nice thing about these checks is that this method is that it works for any connectivity. We start with some payload, we identify the accessible resources to us to implement the checks, and then we can run the algorithm and find suitable checks. And now just to visually see how a circuit with checks looks like, we have these green and blue qubits as our payload, and the red qubits are the check qubits. And now this is time. You can think of this basically as our circuit. And as you can see, the checks are localized in space, but they are distributed in time. They can detect errors that happen before in the circuit in a very efficient way. So again, if you see here, all the red gates, which are the check gates, are local. We are not introducing any swaps for routing or anything. So this is the circuit. The blue region is the original circuit, and the reds are just added gates for the checks. So let's look at some experiments. So we use this algorithm on an IBM Heron R2 QPU, IBM Kingston, to create highly entangled graph estates with increasing complexity. So as you can see, with added checks, the post-selection rate goes down. And this is expected. This is the price we pay to catch errors. And the estimated fidelity increases. So this is the figure of merit. A higher fidelity state is what we are looking for. But as you can also see, there is a place that this fidelity gain plateaus. And that's where added checks are adding more errors than what they can detect. So at some point, we have to stop. And now if we look at the added gates to implement these checks, you can see that the overhead is really mild. So in the largest example, we start with 2,500 gates. And with 9 checks, the total number of CZ gates still doesn't exceed 3,000. It's very mild. And so as you can see, with added checks, we can improve the fidelity significantly. And this comes with a sampling cost, but that sampling cost is more efficient than other error mitigation techniques. So we can look at other applications. For example, preparation of a GHZ state. So GHZ states are a common benchmark for the quality of quantum hardware and software. They can be prepared by short-depth circuits, basically using a breadth-first search from a root of a tree. So we start from this green qubit here and just grow our GHZ state. Then GHZ state, as we saw in the previous talk by Micah, these are equal superpositions of all 0 and all 1. So we can just grow this state. And coherent Pauli checks on these states are very simple. Because the state has this permutation symmetry, it's all 0 and all 1. It doesn't matter which qubit is 0, which qubit. There's a permutation symmetry. It's very easy to look for checks. And also, the checks are low-weight ZZ stabilizers. So if we measure ZZ between any two qubits, this is a valid check. But at the same time, not all checks are the same in terms of the coverage, in terms of their quality. Maybe we add a check and it doesn't catch many errors, and another check catches a lot of errors. So we want to optimize this coverage, and we can use the technique that we introduced to implement very efficient, high-quality checks. And again, in the afternoon tutorial, we will experiment with this application. You will create a GHZ state using these checks. So again, I encourage you to check out that tutorial. So let's get into the details of how we actually create an error-detected GHZ state. So as I mentioned, we start from the root and grow the tree, grow our GHZ state with a breadth-first search. But we don't want to cover the whole device with our GHZ state. We want to leave some space to implement checks. And we do that by selecting some qubits, some nodes, and randomly and block them. So this forces the GHZ support to go around those blocked nodes, and this creates some ancilla space for us. Then we apply these parity checks using those ancillas. Basically, we use the ancilla here to measure ZZ, Pauli ZZ expectation value on these two qubits, and these two qubits, and so on. Because the GHZ state is a stabilizer state, and ZZs are the stabilizers, all of these should be 1. So if we see a ZZ that is not 1, it means that there has been an error, and we can discard that shot. And we can also use the tools that I mentioned to evaluate the circuit coverage for each of these randomized trials and select the best one. There's also one additional ingredient that we throw in here, which is the root qubit uncomputation. So as early as possible, we'll try to uncompute the root and then bring it back to the circuit as late as possible. The reason is that the qubits that are in the state can decohere. But if we uncompute them early on, they can be in the ground state and protected, and then later on we will bring them back in. So this will extend the lifetime of the state. So this tool has led us to create a record-breaking GHZ state on 120 qubits. So if we look at the fidelity of this state, the fidelity above 0.5, this threshold of 0.5, means that we have created a genuinely entangled state. And we have reached that. This was a month ago. And in fact, we have been able to break our own record a couple of weeks ago. And now we have created a 140-qubit GHZ state on IBM Boston. So again, I encourage you to check out the tutorial and experiment with these techniques yourself. So what's next? So I told you about this great tool that we can use to detect errors. But as we also saw, there is a plateau region, and this cannot give us bias-free expectation values. It can improve the quality, but there is a limit. So the natural next step is to apply PEC in addition to error detection. And we have a combined overhead that it scales both with the post-selection rate and the overhead of the PEC. But it would be more efficient to use this hybrid method as opposed to applying PEC alone because of this quartic difference that I mentioned earlier. So this is the work in progress. We are working on it. We're very excited about it. And so stay tuned for updates on this. Yeah. OK. So in conclusion, we talked about error detection in Clifford-dominated circuits inspired by space-time codes. We developed tools that allow us to find valid checks and score them. And this crucially works for any qubit connectivity graph. And as we saw, we have been able to create highly entangled states with 2,500 gates or 100-plus qubit GHZ state in very large experiments. But there are still open questions. So far, we've been using these Pauli checks to only detect errors and discard samples. An interesting question is if we can pick checks such that we can correct errors and don't discard the shots. It is also interesting to explore and see if we can exploit more structure in the circuits and design better checks. For specific applications, maybe there are other symmetries that we can check efficiently using this space-time formalism and perform error detection. And finally, can we apply quantum error mitigation, such as PEC, and checks on a larger scale non-Clifford circuits? This is what we're actively working on, and we're excited about these directions. All right. Thank you so much.